Well, that's what I meant. It's okay. I'll introduce myself. Okay, so thank you to the organizers for the invitation to speak. So as the title says, this is to do with force balance. So it's touching on some of the issues that we heard from Johannes and Rob yesterday, so there'll be a bit of overlap with what they talked about. But there's a new direction as well. So this is work that I've been doing for a few years with Fausto Catania from the University of Chicago. If you're interested in the details, there's a bunch of papers. And the force balance one is really this one, the second JFM one. Okay. So I should mention the main thing that we're going to do, which is inertia-free dynamos. Okay, and I'll explain what that means when we come to it. Okay, so this is not a geodynamo talk. That's my disclaimer. As you'll see, the geometry we look at makes it absolutely not a geodynamo talk, but it is a talk motivated by consideration of rapidly rotating dynamos. Okay. So if we consider the geodynamo, then there's two small parameters, as we know, the Rossby number and the Ekman number. So the Rossby number is essentially the inertial to Coriolis forces, and we can estimate it, as we heard in a few talks already. We have some estimate of the very slow speed in the Earth's core, and a very good estimate, of course, of the depth of the outer core, giving something like 10 to the minus 6. And the Ekman number, I suppose the quantity we don't know quite so well is the viscosity, but the number that everyone always quotes for the Earth, the outer core of the Earth, is 10 to the minus 15. So these are two extremely small numbers. And so you'd like to tackle dynamos for which these two numbers are very small. So it's worth just having a quick look. I know we sort of know all this, at what convection looks like at very small Ekman number, hydrodynamic convection at small Ekman number. So this is sort of classical theory that you could find in Chandrasekhar's book, for example. So in rapidly rotating hydrodynamics with no field, then the balance, so rapidly rotating that I'm ignoring inertia, then the balance has to be between viscous, Archimedean buoyancy forces and Coriolis forces, so called VMAC balance. And as we know, the column width is very small. The column width scales as Ekman number to the third. Given that the Ekman number is huge, the Ekman number to the third, Ekman number is tiny, the Ekman number to the third is still pretty tiny. So if you work this out, what scale do you get? Something pretty small, of the order of, size of this room or something, the order of 20 meters, okay, for the column width. And that's problematic. That's problematic for dynamos. It's problematic because the magnetic Reynolds number on that scale is really small, okay? So on that scale, the magnetic Reynolds number is only like 10 to the minus 2, okay? Whereas, I know we had this discussion the other day, it's hard to know, there is no absolute criterion for, the Reynolds number has to be something for a dynamo, but experience shows that you need a magnetic Reynolds number of the order of hundreds to thousands to get a decent dynamo. So there's a lot of orders of magnitude missing here, okay? So it's very, very hard to argue that the Earth's dynamo is driven essentially by columnar convection, okay? So this is where the whole issue of the balance has come in, really. I mean, if this worked, we'd all be happy. So to get this number bigger than 10 to the minus 2, you can't do much about. I mean, U is known, more or less, or at least estimated. L is definitely known. Sorry, eta is known, more or less. L is not known. L is the scale of the convection. And so that's the thing that you've got to change if you want to get this number bigger. Okay, so the idea, of course, is that this is not what the flow looks like at all. It's on much, much bigger scales. And scales in which the magnetic field makes the scale large. And because the scale is large, the viscous force isn't so important. And that then you might have a dynamo in so-called MAC balance. Okay, sometimes known as strong field solutions, sometimes known as Taylor states. Okay. And of course, as we all know, finding these things is not easy. Now you might say, isn't that a wishful thinking? Why should we even think that the magnetic field is going to be so nice as to get us out of this mess? So really the idea of strong field dynamos, I think, came about probably through an analogy with the simpler problem, which is rotating magnetic convection. So this is a classical problem, Boostinesque, rotating convection with an imposed vertical field, let's say. You can find this in Chandrasekhar's book. It was studied by Ibrahim El-Tayeb and Paul Roberts in the 70s. There's a very nice paper. There's a short paper by El-Tayeb and Roberts. There's a very nice longer paper by El-Tayeb covering this problem in Filtrans in 72. So the problem has 3 dimensionless parameters: Rayleigh number, Ekman number, Chandrasekhar number. Rayleigh number measured the driving, Chandrasekhar number, let's say, a measured field strength. And each of the extreme problems, so if you have no magnetic field, then as we've just seen, you get very small cells and a very high critical Rayleigh number. Okay. Conversely, at the other end, with just a magnetic field and no rotation, you also get very small, so high Q, you get very small cells and a high critical Rayleigh number. Interestingly, putting them together, the strong field can enhance. If you put the strong field into the rapidly rotating convection problem, then you can lower the Rayleigh number. You can lower the critical Rayleigh number from Ekman to the -4/3 to Ekman to the -1 at a certain Q. And crucially, you shift the scale. You shift the scale all the way from e to the -3 all the way to order 1. Okay. And interestingly, this is one way. You have to put the field into the convection to do this. You can't put the rotation into the magnetic convection. That is always stabilizing. Okay. And so the question is, you know, when you don't have the field at your disposal, can the field, by being self-generated, be such as to change the convection to keep the dynamo going? Okay. Everyone has to be in this together. You have to generate the field that changes the convection that keeps the field going. Okay, that's the hope, of course. And this is a diagram we have seen many times already. It's in a book which is very hard to come by, or at least I find it very hard to come by, in an article by Paul Roberts. And it has, you know, we've seen this a few times, the weak field and the strong field branch. And of course, you can find it again in Keith and Emmanuel's book as well. So the idea is, you know, if there were a weak field dynamo, it would come off here, but what we're looking for is a strong field dynamo. Okay, this is some measure of the field strength that is not connected to the weak field dynamo at all. This would be a dynamo coming from the small scale convection. Okay, whereas this is the strong field dynamo at large spatial scales. Okay, and the Earth sits there on this diagram, somewhere in there. So what can you do? Well, we've heard quite a lot of what you can do to model dynamos at low Rossby number, low Ekman number. I think there's 3 things. roughly, you can do. So one is, as we've heard, seen examples of, you can solve the full equations, okay? And you can push the parameters towards the Earth in various directions. You know, you can reduce the Ekman number, for example. And so you know, obviously the trend has been to keep reducing the Ekman number. These heroic calculations can get down to about 10 to the minus 7 possibly. And the hope, of course, is that they will start turning into the, you know, Earth-like regime. I think even at Ekman numbers of 10 to the minus 6, they're not particularly Earth-like, okay? In the sense that they're not MAC. Viscous and inertial terms are still important. And I think the recent ones possibly show some evidence of MAC balance. So there's a lot of very impressive work being done in that direction. Okay, you can make your life easier, which is what I'm going to talk about. So you can discard inertia from the outset. Okay, so all the balances, say that some of the balances Johannes was mentioning yesterday that had, you know, I in the title, CIA, whatever. I don't have any I, okay. But you keep the viscous terms, okay. So that's what we're going to do, okay. So you say rotation is always so rapid that I can get rid of inertia, but I'm going to keep the viscous terms, partly for numerical reasons, but partly to assess how important they are, okay. Or, which of course in some sense is what you want to do, is throw everything away. You want to throw inertia away and you want to throw viscous terms away from the outset. And that of course is an idea that goes back to this pioneering paper by Brian Taylor in the 60s. I know most of you know this. If you do that, of course, this is the equation you get from the, well, you can call it the momentum equation. There is no momentum in it anymore. It's just an instantaneous force balance. Okay, there's no inertia, there's no viscosity. With that equation, you have to have this constraint, so-called Talus constraint. Okay, and Taylor in his 63 paper put forward a very nice algorithmic approach as to how you should solve the dynamo problem whilst maintaining his constraint. My understanding is that that has proved extremely difficult to implement, except there are some mean field models in which it can be done. I don't think it's, I know there are people that have worked on this. I don't think that it's been entirely successful as yet. It's a very difficult problem to study in this way. Okay, so this is what I'm going to do. So when I said it's not a geodynamo talk, this is why it's certainly not a geodynamo talk. Okay, we're going to look at a much simpler geometry. We're going to look at a plane layer, rotating convection problem. It's about the simplest convection dynamo you can look at. Dynamos in this geometry date back to Childress and Soward, for example, in the 70s. I think they were the first people to look at this. So let me just tell you what the setup is. It's a 3D Cartesian layer. It's Bousson-esque, and it's rotating about the vertical. We have an aspect ratio lambda, and the boundary conditions are, what's the word? Illustrative, is that the word? They're as simple as we can make them, okay? So they're stress-free, they're impermeable, they're fixed temperature, they're perfectly electrically conducting, okay? And the key thing that we do is we neglect inertia. So this is a model that has been looked at before. Chris Jones and Paul Roberts looked at this in this paper in JFM. It's not received a huge amount of attention since then, so I think it's quite an interesting model. So the equations, I know we've seen equations, but it's good to know exactly what the equations are for this system. Okay, so there's no inertia term. There's no dtu plus u dot grad u. That is our assumption that it's gone. Okay. But there is the viscous term. The induction equation. So we scale things with the thermal time here. So kappa over d squared or d squared over kappa. That's the time. So we have no coefficient in the temperature equation, and we have 1 over q. Q is what is often known as the Roberts number in front of the del squared b. Okay, so those are the equations we solve. In terms of how you'd solve them, of course, you can only advance the magnetic field equation and the temperature equation, and you have to solve for the velocity. Okay, but you don't have Talus constraint or anything because you have this term, so you can do that. So the input parameters, there's the Ekman number. It's easier, traditional in these things to work with a modified Rayleigh number where you have the rotation underneath, which is related to the normal Rayleigh number like this, and there's the Roberts number. There's no Prandtl number, okay, in this problem. So what is this inertialist system? So if you didn't throw away the inertia and you kept it and you used this scaling, its coefficient would be E over PR. So in some of the talks we've heard in this meeting, it's been E over PM, but that's because the scaling is done with the magnetic diffusion rather than the thermal diffusion. Okay, so you can, mathematically, you can think of this as the neglector inertia as infinite Prandtl number convection. And it's sometimes billed as infinite Prandtl number convection. Slightly misleading in a way, because people then start saying, but does that mean your viscosity is infinite and things like that? And the answer is no, it means the Prandtl number is infinite. But what it really is, of course, is a small Rossby number expansion. That's really what it is. Okay. Technical point, I think Andy raised this on Monday, maybe. The idea of energies is slightly strange in this problem. So that if you work out the magnetic energy to the kinetic energy, so this would be it. These would be the dimensionless numbers, the B and the U, under this scaling. Then it comes out like this. But the Prandtl number is infinite in this problem. Okay. So you cannot relate magnetic energy to kinetic energy in this problem. Maybe it's not that surprising because what does kinetic energy mean? You know, we have no dtu to give us a kinetic energy equation. Okay, so and what's left? What have we thrown away? Well, if you look at this just in terms of waves, for example, on a uniform magnetic field, these are the only waves that are supported. Okay, so there are these interesting hybrid waves, which involve both the alphane frequency and the inertial frequency. Okay, so these are what, just in terms of terminology, I think Atchison and Hyde called them hydromagnetic inertial. I think in Keith's book, he calls them magnetostrophic. And what you lose are the pure inertial waves. Okay. So computationally as well, infinite Prandtl number is useful. You're not chasing any high frequency waves around. Okay. The inertialist system also has a nice property. So one of the reasons we looked at it was we were trying to understand things like how does the dynamo saturate, which is quite a hard question to get a grip on. But in the inertialist system, of course, what I'll call the momentum equation, for want of a better name, is linear in U. It's only got the Coriolis term. And so a useful, non-unique, but nonetheless useful decomposition is to split your velocity into what you might call a thermal velocity and what you might call a magnetic velocity. Okay, so if you add these two together, of course, you get back to the momentum equation. So the thermal velocity doesn't have the magnetic field in it, and the magnetic field velocity does not have the temperature in it, the buoyancy term, okay? We make them both solenoidal. Their sum has to be solenoidal. It would be slightly perverse not to have them individually solenoidal. They're not quite as separated as you might think at first sight, because theta, okay, the temperature depends on the whole velocity, including the magnetic field. Okay, so so the field does enter ut via this theta, because in the theta equation we use the full u, of course. Okay, so they're not quite as uncoupled as they look at first glance. So through this decomposition, we define two sorts of dynamo. Okay, what we're going to call weak field dynamos and strong field dynamos. So the weak field dynamos, this is how we're going to do it. The weak field dynamos, the thermal velocity I'm not sure I've written that quite right. The thermal velocity, differs. That's right. Sorry, I have. The thermal velocity differs little from the kinematic velocity, and um is small. So a weak field dynamo is where you start off with a flow, it evolves, and the flow doesn't really change much. Of course it changes, because if it didn't change, you wouldn't saturate the dynamo, but the changes are small. So um is small compared to ut, okay? Or a strong field dynamo, where is significant, okay? Now, Rob was talking about this yesterday. This weak field dynamo does not necessarily mean that it's on the weak field branch in that plot I showed from Roberts, okay? This, I believe, is what Rob called not a strong field dynamo, okay? So, but for the purposes of this talk, I'm calling a weak field dynamo one where the flow is not changed significantly by the saturated field, and a strong field dynamo as one in which it is, okay? Oh yeah, that's right. You can also, which is a useful comparison, come up with another problem. So I just said that you've got the thermal velocity and the magnetic velocity equations. They are coupled. You could come up with a problem where they're not really coupled. So you could have what we call a thermokinematic problem, where the temperature really is driven by the thermal velocity. So this is as if you had a forcing, right? You could imagine driving a dynamo with a forcing where the forcing was completely independent of the field, right? It would.
Which velocity describes large-scale separation? Thermal velocity?
Well, the whole velocity describes, yeah, the sum of the two. I'm just putting, at the moment, I'm just describing a comparison problem. So a comparison problem, which is an artificial problem, doesn't mean that it's not worth looking at. It's a problem where the forcing is independent of the field. So we force it with the convection, the small scale convection. Okay, it will still be a dynamo, or it could be a dynamo, and it will saturate. But the temperature it's always driven by this small scale. Okay, so the way to think of this thermokinematic problem is a forced dynamo where the field does not affect the force, and the forcing in this case is just the convective forcing. Okay. So you see in the full system, you can have a large scale magnetic velocity, and that can drive a large scale theta, and hence a large scale thermal velocity, but not in this constrained problem. Okay. Right. So let me show you what's going on. So these are just some illustrative, this is what inertialist convection looks like. So these are low, but not cosmically low Ekman numbers. So if you're fairly close to onset, of course, then the cell size is really governed by the e to the minus third. As you move away, so this is increasing the Rayleigh number. This is the the modified Rayleigh number. As you increase the Rayleigh number, of course, you become less rotationally constrained, even though you are always rotationally constrained in this problem because I've thrown away inertia. Then you go from these small cells to bigger cells, and you start getting, you can see here, this is a cross section at the bottom. They really are these columns, but they go into these sort of sheets as the rotational constraint is weakened somewhat. So we're going to look at dynamos in these cases, okay? And then we're going to look at the force balance of dynamos in these cases. So this is a dynamo driven by this flow, okay? The flow on the right. So this plot is like a generic sort of plot. As I said, these numbers, this number compared to this number makes no sense. You cannot compare these numbers. In fact, to put them on the same plot, you multiply it by some vast number. So you should not think that, you should not compare that with that, okay? But this measure of u squared decreases as b squared increases. That is a canonical picture of dynamos and dynamo saturations, okay? This is what the flows look like. So this is the kinematic flow. And this is when it saturates, snapshots. But you can see that not much is, in terms of scale, not a whole lot has changed, okay? This is a better way of looking at it. This is a spectrum, a horizontal spectrum of the two flows, time averaged. The solid line is the kinematic spectrum, so there's a peak here. And you can see there is some movement to larger scales, okay? So the flow there is some indication of a larger scale flow here, okay? In terms of whether it's a weak field or a strong field dynamo, so this is the full vertical velocity at a snapshot. They always look, doesn't matter whether it's a snapshot, they always look kind of like this. This is the thermal velocity, and this is the magnetic velocity. So in my terminology, this is manifestly a weak field dynamo because the thermal velocity and the full velocity are almost the same. These little blobs here are all that the magnetic velocity does. Of course, the magnetic velocity is saturating the whole thing, so it's important, but it's only important in a few tiny bits that stop the dynamo growing. You might say that's a cheat in that dynamos don't really know about velocities. They know about velocity gradients, in which case you should look at these three. This is the vorticity for the same thing. So these three are to be compared. This is just a generic kinematic, just a snapshot at some stage in the kinematic evolution. These three are all in the dynamic regime. So this is the vorticity, the vertical component of vorticity. This is the thermal vorticity, which has no sharp features. And the magnetic vorticity, so this is sort of interesting, how it saturates the dynamo is through these vortex sheets, the formation of vortex sheets at the edge of these vortex cores. Okay, so there's a clear distinction in these two. Okay. Okay, so that's what a weak field dynamo looks like. What does a strong field dynamo look like? Well, this is what happens. This doesn't tell you it's a strong field dynamo. It tells you something is happening, though. It tells you that there's a huge change in the velocity, the form of the velocity, as the field saturates. In fact, the velocity becomes, this measure of the velocity becomes bigger, okay? I'm reluctant to call it kinetic energy, so I'll call it average of u squared increases as the dynamo, as the magnetic energy increases, okay? So if we play the same game, this is the kinematic flow field, and this is the dynamic one where you can see there's kind of much larger scales emerging here. And if you look at this plot, you really can see it. Okay, so this is the solid line is the kinematic velocity field. It has a well-defined peak, which is those little cells have that wave number, okay, 30 or whatever. And you can see there is a shift in the large scale component, or an increase in the large scale component of about 4 orders of magnitude. So that in some sense is good if you're on the hunt for max solutions, if you're on the hunt for Taylor states, that is good. What is not good is this, because this is increasing the energy at small scales. If this were an out and out max solution, it would look something like this, and then it would just come hurtling down. Okay, so we'll come back to that.
You mean kinematic? It means that there is no back reaction of magnetic field to flow.
Yes.
Correct?
Okay. So by kinematic, yeah, I mean, really, I mean, this is even before we put the seed field in. This is so we have a velocity driven by convection, which has those small scales, and the small scale is given by that wave number. Then we put a seed field in, it grows, it saturates, and its spectrum, time averaged, is given by that. And we can look again at these. So this is definitely a strong field dynamo. You can see that this is the full velocity, this is the thermal velocity, which is taking a back seat in some sense, except it's driving the whole thing. And this is the magnetic velocity, which looks more or less like the full velocity. If you push it even to a lower Ekman number, higher rotation rate, so if you decrease the Ekman number to 10 to the -5, then the velocity is nearly all magnetic. It's quite interesting because it's a convectively driven dynamo. So this remnant is what's driving it, but what remains is this magnetic velocity. Okay. Right. So the interest, as we've already heard yesterday, there is interest in these. Once you've got a dynamo, what does it look like? How do you categorize it? What is the balance of forces in the equation? Okay. So our view, which was also stated yesterday, but our view is that you should look at the vorticity equation. You should not look at the momentum equation. Nor the velocity equation. The velocity equation has pressure in it, and it has all sorts of other bits that are gradient terms. They keep div equals 0. In an incompressible fluid, they keep div equals 0. They are not of dynamical significance. Much better to study the vorticity equation. However, numerically, that's problematic, in the sense that typically one runs these things to make sure your current is resolved. Typically, one does not run these things to make sure that the curl of J cross B is resolved. That's giving yourself a lot of spare capacity. So if in these calculations, we calculate, so if we took we could do it, obviously, in theory. We could easily look at the curl of all these terms, but the curl of J cross B has, of course, brings in another wave number in a spectral code that just kills you. Yes, sir.
So you solve the vorticity equation for the curve?
No.
You solve it, so you solve for the pressure?
No.
What do you solve?
We solve for the velocity and project.
You solve for the pressure.
Yes and no. So what you do.
Very accurate spectral curve.
Yeah.
I don't see the problem.
You don't? The problem is because yeah, you've got an accurate spectral code, which you push to the limits of the accuracy, right? So your J is resolved. Your J cross B is resolved, because you need to have that. That doesn't mean the curl of J cross B is resolved, because that's bringing in another K, and a very high K.
And I understand. I mean, it depends on the nature of the spectrum. You've just shown you've got a flat spectrum, so you've got a problem. But if you've got a decaying spectrum, that's no problem. So,
Well, the spectrum we have goes way beyond that picture. Of course, that was not the full spectrum of this simulation. From experience, I know that if we work out curl of J cross B, it is not, we were not happy with that. You know, you start getting ringing and things, and yeah, we were not happy. But no, we don't solve the vorticity equation. That's one of the beauties of Boussinesq spectrum. You can, so all you do is you advance the velocity, right? Well, of course we don't in this code, but in general, you would advance the velocity and it would be non-soelnoidal, and then you project. But the projection operator is well behaved. You don't have to deal with pressure. I mean, pressure is a Lagrange multiplier, isn't it? And that's how you deal with it. I mean, there's various ways you can deal with it, but no, we did look at curl of J cross B, because we thought, the vorticity is what you should be looking at, and we were not happy with it. So that was so instead, what we do instead is project. So you can project onto the soleноidal components. And why that's much better behaved in a spectral code. The projection operator looks like something like identity minus ki kj over k squared. There is no big k's floating around. So that's a much better behaved operator. So that's what we do. So we consider the two equations where we project them. Okay. The drawback is that it's not so intuitive, in that the solenoidal projection of a vertical force, for example, like buoyancy, is not vertical. Okay. So in our force balance, in our analysis of the force balance, we've got 6 terms here, okay, which we're going to look at, and we're going to look at the vertical and horizontal components of those 6 terms. Okay, so this is the thermal equation, this is the magnetic equation projected onto their solenoidal components, horizontal and vertical. I think that's 12 things to look at, unfortunately. So these are they. So of course, even this, so this is a measure of the forces. Even this you have to be a little bit careful, of course, because they're forces that they're not necessarily aligned, even if they've got the same magnitude. So we'll come back to that. So what's going on in these things? So on the left are the vertical projections, on the right are the horizontal projections. The red is the thermal velocity equation, the blue is the magnetic velocity equation. So what you can see, let's look at this one. So in the weak field dynamo, okay, viscosity is still important in the thermal equations. The interesting thing that you can really see is that as you go from weak to strong to super strong, this term, which is this term, the viscosity in the thermal equation goes to 0. So in terms of, can we throw away viscosity when we're in the, when we're in the rapidly rotating limit? Can you have a dynamo where you throw away viscosity? I would say yes, in that equation. Okay, but if it were Taylor, I would have to throw it away in this equation as well. Okay, if I was really going to get rid of viscosity, it would vanish here. And it doesn't vanish there at all. It becomes big here. So these dynamos that we're finding, they are strong field dynamos, but they are not Taylor states, and they're nothing like Taylor states. Okay. So I think I probably just said that. So the viscous terms remain important. Okay. So they're strong, but they're not MAC. So if you wanted to categorize them, you could. So I reckon whoops, what am I doing? So you could get rid of this one, but you can't get rid of that one. Okay. So it's interesting to see what's going on, as well as just looking at the magnitude of these forces. It's interesting actually to see what they look like. So this is a weak field dynamo thermal equation. Okay, so this is this bit. Okay, but now we're looking actually at a slice of the projected forces. So you can see they are of the same ilk, right? You can see the same pattern, but they're not the same. The difference between them is accommodated by the viscous term. So the viscous term here is crucial, right? The viscous term takes up all the difference between these two, as you might expect. However, in a strong field dynamo, this is the projection of the Coriolis force. This is the projection of the buoyancy force. They are essentially the same. There is very little for the viscosity to do. The viscosity takes up the difference between them, but there is almost no difference between them. So that's what I'm saying. I think as you push down stronger and stronger in the thermal equation, you're happy to throw away viscosity. Okay. In the magnetic equation, this is the Coriolis, and this is the magnetic tension. Okay, again, you can see the same kind of general form, but boy, you know, the difference between these two is huge and is accommodated by viscosity. That's the weak field dynamo. The hope, if there'd been a hope, would be that we might, in the stronger field case, maybe that wouldn't be the case, but it is. So this is a strong field dynamo. So this is the projection of the Coriolis force in the magnetic equation. This is the projection of the magnetic force in the magnetic velocity equation. Were this to be a max state, those two should look the same. The difference between them has to be accommodated by viscosity, and the difference between them is significant, obviously, with these very strong current sheets here. Okay. Oh, that's just a blow up. Okay, sorry, I'll wrap up shortly. Just a quick thing to say about this thermokinematic problem that we introduced. What's the main difference? So the main difference is in the thermal velocity. So this is the full system, and you can see the thermal velocity gets up to, let's say, 60, here, 70. Whereas in the thermokinematic, it's struggling. It's not getting very high in comparison. So what's going on? So in the full system, there are two ways that the magnetic field can act on the temperature in two ways. Okay. It can generate sort of counter vorticity on the scale of the initial cells, but it can also shift the velocity, thermal velocity, to large scales. In the thermokinematic problem, that's exactly what the second of those is exactly what you're not allowing. You're always forcing on the small scale. You're not allowing it to go to large scales. So you're not allowing it to breathe freely, okay? So you can see a consequence of that is in the convective heat flux in these dynamos. So this one, TK, thermokinematic, that's the heat flux of convection. So if you forget magnetic field, that is the heat, convective heat flux of the rotating convection with no field. And this top one is the convective heat flux, Nusselt number if you want, of the magnetic problem. So there is a considerable, it's way more efficient as a transporter. So it's relaxed into this state where it's convecting more happily. It's got a large scale field. Okay. So just, I've probably said most of this. So we have weak and strong field solutions. They're not MAC. If you wanted a snappy algorithm, this is not it. So in other words, that you have to keep the viscous term in the magnetic equation with the MAC. Okay. You might say, could you, if we found a Taylor solution, suppose we locked onto one, whatever, constructed one, would it be stable? We think not in our regime, because if you gave it a small scale perturbation in B, then you get small scale Lorentz forces, you get small scale flow, etc. Okay, and the small scale fields are maintained. And so even if you constructed yourself a large scale Taylor state, it would not be stable in this regime. How might you get one? So you have to go all the way, push yourself all the way down the subcritical branch until there is no field generation on the smallest scales you can think of. Because if there is, then you will always get small scale fields, and viscosity on those scales will always be important. On that note, I'll finish. Thank you.
Okay, we're eating into coffee time, but we have time for a small number of questions, just for 2 or 3 minutes.
In the presence of inertia term, you cannot easily decompose to the thermal and magnetic velocity. Is it correct?
Indeed not. Because you've got u dot grad u, and so you're stymied.
The second question, why magnetic fields strongly increase thermal heat loss?
Oh, because they allow the convection to completely change shape. So they allow it to go from the like the Taylor columns, if you like, which have a certain amount of heat. They convect, but they're not phenomenally efficient at transporting heat. But the magnetic field allows the convection to take on much bigger cell size, which carries way more heat. As well, it does it all. It's great. It does more convection, which keeps the field going, which keeps the convection going. Everyone's happy.
Yeah, David, in the beginning, you mentioned that the UT and UM, they're not really as separated as you would want them to be. My impression is the pressure could be a problem here, because that's kind of, I don't know what you use there, kind of arbitrary. How do you separate PT and PM really?
As I say, we kept them both soelnoidal.
Yeah.
So that determines PT and PM.
But you could just, take something out PT and throw it into PM.
Of course.
And that, that means it's just not unique what you're showing here. So you would like to actually look at the curl for that reason, right? Then the pressure is not a problem anymore. But you said that is a problem because you were not satisfied when looking at the curl of the first balances, right? And that's probably a resolution problem, I would say. So if you would push the resolution higher, then, this is always a problem. So you solve a force balance, right? When you solve a force balance and you want to check a vorticity balance, obviously you're not solving for that. So there may be numerical issues here. Mm-hmm. And so if you do that, you should check closely whether the vorticity balance is still fulfilled and to which degree, right? But you can get, well, of course, increasing the resolution will always help there, right?
Yeah, I mean, if you've got enough capacity spare capacity that you can always work out the Lorentz force accurately, then you can do that.
So the computer is really the limit for you here in the moment.
Well, or you do. Yeah, I think if you had infinite capacity, you would use the vorticity equation. I mean, that's still an important point. I would always use the vorticity equation. I wouldn't faff around with the momentum equation. I think that's misleading. So this is an alternative way of looking at it, which is more accurate if you don't have infinite capacity. I don't think many people do have infinite capacity on their computer.
I can see there are other questions, but I think we should break and you can ask them over coffee. We will start again about 11:15, probably slightly later, 11:20.